The last type of titration curve that we could see would be involving a polyprotic acid. So instead of just one hydrogen reacting with our hydroxide, we have multiple hydrogens that can be removed. And when we look at this graph, we see multiple jumps in pH as the first hydrogen ion is removed, the second, and the third. You won't have to do calculations for all of the different versions and places that could happen here. But do remember that just an equivalence point calculation itself is possible for any combination of strong with weak. But when it's polyprotic, it's really important to pay attention to the mole ratios. What you would likely be more asked about would be the predominant species. That means, what do we have the most of at these different times? As we go along, it's really tempting to think about we're adding more and more hydroxide ion, that we at some point would have an excess of hydroxide. But remember, we don't have an excess of hydroxide until we've totally removed all of our hydrogens, or totally neutralized every part of our acid. So even though we're adding hydroxide and adding it, we don't get to an excess of hydroxide until after our third equivalence point. The initial acid in this case is phosphoric with 3 hydrogens. So at the very beginning, obviously we have the most of that. And at the first equivalence point is when we've converted all of our H3PO4 to H2PO4. So this is where we have no more H3PO4 and it's all turned into H2PO4. The midpoints, or the half equivalence points, are super important as well. Understanding if this is all H3PO4 and this is all H2PO4, this is where they're equal to one another, once again with our pH equal to our pKa1. So if we're thinking about just something like phosphoric acid in solution, then, or in this initial one, we would have so much of our initial H3PO4 relative to any other ions. As we go through this reaction, we would be thinking about that hydroxide allows this to go to completion. So here, my H3PO4 is gone, and it's all H2PO4, which is turning into HPO42 minus. There, the H2PO4 is gone, and it's turned all into HPO42 minus. Here is where that is gone, and we finally turned into just the phosphate ion, and then we're ready to have an excess of hydroxide. So lots of different things going on here. Our pHs and our pKas, these go back to the pKa values that were given way earlier in the notes, so you can make those comparisons there. But just understanding that it's a one step at a time process, thinking about totally our first acid with very little ionization, then at the equivalence point, we've turned into our product. And halfway is where they are equal to one another in terms of the acid that we're looking at with its conjugate base. There are a few bases that can accept more than one hydrogen ion, the carbonate ion, for example, and they would look similar to this, just kind of going down one hump at a time.